Welcome
Hi, guys.
to another episode of Eigenbros, folks. Today we're going to talk about circuitry,
Yes, electrical circuits.
electrical circuits, a little bit about how to rebuild society in case, the coronavirus outbreak cripples the population and you have to rebuild your hometown.
Right, you got to know electricity.
You got to know how to, you got to impress the ladies or impress the men, depending on which way,
Why not both?
Why not both? Hey, why not both? And so we talk a little bit about the physical principles behind circuitry and how to maybe we analogize them to kind of give you this better sense or intuition of the stuff. And then we kind of go into the deeper physics of it, right? We kind of go into maybe how you can think about it in relativity, or how relativity sort of interprets, I guess, this kind of physics that goes on.
Yeah, we talked about relativity, I guess, in terms of moving charges.
Right.
Yeah, and that sounds like a pretty good synopsis. Also talked about Faraday's law, parallel circuits, series circuits, Ampere's law.
Yeah, towards the end, we kind of cover like the more general physics concepts, Maxwell's equations, how they relate to that.
Yeah.
And then we kind of get into like maybe a meta, just talking about the actual podcast a little bit.
Sure.
Yeah. So stick around if you want to sort of. It's a sort of survey that we give at the end of the podcast, and we definitely want you guys to answer that question if you can. Tweet at us at Eigenbros. Email us. I think we have an email account, right? At eigenbros.com.
Yeah, we do.
I mean, at gmail.com. Well, eigenbros at gmail.com.
Let me do the shout-outs.
Yeah, this is why I don't do it. Stuff. Okay, he's the brand manager. So.
Yeah, so we do. We got eigenbros.com is the website. We got at Eigenbros at Twitter. We got Eigenbros on Instagram. We have Eigenbros2 on TikTok. And I think that's it, guys. There's the mailing list on the website, but it's messed up. So we'll have to fix that at some point.
Yeah. So check that out. And let us know what you think.
All right, guys.
All right. 3, 2, 1. Coronavirus is here.
Dun, dun, dun.
Yeah, man. We're unrelated, though. Today we'll be talking about circuitry.
Yes. So electrical circuits. I thought it'd be a nice one to do for the audience. Get some physics in there.
Get your mind off of more drastic things happening in the world around us right now.
I know you're concerned about Corona. I'm not so concerned, though. But
let's spend like 5 minutes on it.
Yeah.
Just so people know what's going on.
Sure.
In case you're living under a rock these days. Corona right now this is going to be released around
Friday.
Yeah, Friday, March March, can't do math. March 14th.
What's today?
It's Monday. March 9th.
March 9th. Okay, yeah. 14th.
So no, 13th. Sorry.
Is it? I don't know math either. Plus 4. Yeah, 13. Good job.
Ooh, Friday the 13th.
We can do arithmetic. Yeah.
Friday the 13th. Yeah, so.
Oh, shit.
Dun, dun, dun. This is going to be a big deal in the next coming weeks. The coronavirus is already projected, as if you listen to our last episode, which was APS March meeting canceled, we kind of go over
foreshadowing.
It's foreshadowing. Yeah, maybe you can go back to listen to that and see how you're going to be affected by the coronavirus. I think in the next 3 weeks and some of it through April, it's going to be widespread in the U.S. And say goodbye to your loved ones. No, I'm just kidding.
Jesus.
I'm kidding. I know, right? It's so drastic. But seriously, call your parents, make sure they're doing okay. And and if you're probably a university student, wash your hands. Yeah,
I would say everybody wash your hands.
Wash your hands.
Probably advisable.
Yeah, that's the number one thing. And don't want a mutated virus going around, so limit yourself exposure to other people and get good rest, eat healthy, that kind of stuff. And so on to more simple things.
Yeah.
Like circuits. Circuits are kind of interesting because they're.
Here's my
why do physicists even why should I care as a physicist
about circuits?
Okay, why should a layman care about circuits to begin with?
That's a good question. So I guess a layman, it's probably not super critical for them to know all the circuit stuff. But, if you're a curious person and you just want to know more about the modern world, I mean, literally every single building we enter in pretty much has electricity. I'd say probably at least 99% of buildings have electricity, right?
Yeah, and if society collapses, then you might be able to take some of this knowledge.
Yeah.
You might become a fucking wizard.
Exactly. I always love those doomsday scenarios where you have to rebuild society.
Oh, yeah.
And I think as a physicist, it's kind of an interesting thing because we do know so much about the natural world. We probably could recreate a lot of concepts.
Oh, yeah.
Just from scratch.
Yep.
So circuits.
We could rebuild society.
Yeah, I think I could do a pretty decent job at rebuilding society.
Yeah, I talked to a postdoc about this.
Yeah.
And he was a German postdoc. Shout out to Dr. Schoenemann.
Okay.
Yeah, I think I nailed it. He told me, he said, I think I could rebuild society if it collapsed. Not necessarily from the coronavirus, but, any other apocalyptic event in that sense. Because he's like, I know how to build a generator. I know circuitry stuff.
Right.
In principle. And I know it's an engineering problem at that point, but nonetheless, you need to understand the main principles to rebuild society. And honestly, physicists would be a hot commodity in that kind of world.
For sure. Wasn't it a professor on Gilligan's Island who built all the stuff?
Was he a physicist?
I'm not sure if he was a physicist, but for some reason my mind wants to believe he was.
Oh,
I saw it when I was a kid, though, so I didn't know anything about that back then. But yeah, I love that show. Gilligan's Island.
It might be a Mike Jones situation, by the way.
Mike Jones?
I mean? Yeah. Back then, they didn't want me. Now the society has collapsed.
Hot hose, they all on me.
Yeah, now that society's collapsed, they all on me.
Maybe it was. Mike Jones situation. I like that.
Yeah, where it's like you become a hot commodity because your level of knowledge is just too, it's too,
it's in vogue.
It's in vogue.
En vogue, I should say.
You're required. Your talents. You have a particular set of skills.
Yeah.
And that you're very necessary to rebuilding society. And honestly, you would be. I mean, how do I even put this in a nice way?
Yeah.
You would be pretty much the town wizard.
Yeah. Unless there was another physicist. And you have to kill him.
Establish dominance.
Exactly.
Yeah.
Highlander. Can only be one.
Or have a battle of wits.
Yeah.
Who becomes the town dunce? Who doesn't have it? Like you do a challenge like who can solve this crazy integral, and then the town watches like kind of not knowing what's happening.
And then nobody really knows.
But yeah, it's this is an important thing to know off the bat. If let's say there's a contingency where you have to rebuild society, and you need to know circuitry. You need to know how electronics work.
But even though not going that far, we can just say it's useful to know electricity and circuits because it just helps you to understand modern society better. Mm-hmm. Like living in the 21st century, you should know a little bit about electricity. Like if you have kids, you don't want them sticking paper clips into an outlet. Mm-hmm. Because then that's going to short the circuit, and now you can have electrical problems.
Well, besides that, your kid would be dead.
Not necessarily. I did that. Well, my sister did that when she was a kid, and it just caught the electrical socket on fire.
Oh. Yeah.
But we didn't die.
Oh, okay.
So
I was like, did you touch it? And how do you know you're not in hell?
No, she touched it.
Oh, okay.
But she was fine.
I was like,
how do I know I'm dead like Haley Joel Osment or something?
Yeah. I was like, how do you know you're not in hell right now?
Yeah. You're actually the kid from Sixth Sense.
Yeah, I'm his guiding demon.
Yeah.
That's, or angel, I should say.
When I watch the podcast, it's just you talking.
Yeah. Yeah. There's just, I'm having a psychosis.
Right.
A psychotic breakdown. But anyway.
That's the Sixth Sense for those of you who Zoomers out there who don't know that movie.
Spoiler. I actually have never seen it.
Really?
Yeah.
But you got spoiled probably, so you didn't want to watch it, right?
It's one of those things where it's like, I get the point of the movie now.
Yeah.
Yeah.
It's kind of one of those when you know the spoiler, it's a massive, massive spoiler to not even want to watch it.
It's the same thing as Luke, I Am Your Father. It's the same thing.
Mm-hmm. Not as significant,
I guess.
but pretty big still.
Yeah.
Yeah.
But
Anyway, let's get on track.
Let's get. All right, you know what? Let's do it. Circuits.
Yeah. So basically, I just wanted to go over some concepts.
What are the main principles? Because I know I can name like two or three off the top of my head.
What do you got?
Ohm's law.
Ohm's law.
Kirchoff's rules.
Kirchoff's rules.
Let's see how good my undergrad was.
Okay.
There's a third one in there. I don't remember though.
I'm not sure.
Starts
either.
with the V. I don't know.
I don't know.
Okay,
I don't know if I wrote it down.
Let's just say me and Terence have both had the same undergrad education, so that means we both agree these two rules are important.
Yeah, I have some other stuff on there just for like extra. Like I kind of went a little bit deeper, like doing Faraday's law, Ampere's law.
Oh yeah,
that stuff. But that's related to like
E&M.
E&M. But we can delve into that a little bit too if we'd like.
Sure.
But I guess we can start with like Kirchoff's laws. So Kirchoff's laws are pretty useful. It was of course invented by Kirchoff, and
how do you spell that for people who want to Google it?
That's Kirchoff. I think it's German. I want to say.
Yeah.
Not sure though. Don't quote me on that because the double F is kind of weird. I'm not sure if that's German.
I think it's Mexican.
Kirchoff.
No,
Kirchoff.
Kidding. So yeah.
So the Kirchoff's laws. There's two big laws in that, and one of them is known as the loop rule, and then the other one is known as the what is it called? I want to call it the junction rule. Yeah, there we go. So basically, what they're saying is, if you imagine you have a circuit. So what is a circuit? Basically, a circuit is just like if you imagine a wire. So let's say some current carrying wire, like a piece of copper, wrapped in some insulating material.
Yeah.
And, that has some kind of source, like a battery. So it's basically a battery connected at one end. And then there's usually a resistor to make sure that you're not going to burn the circuit. Yeah. So when you have a battery, a wire, a resistor, and then you connect that back to the battery, then you have a complete circuit.
Yeah. So if you're like me, let me preface this. So if you're like me, what Terence just said, just your eyes glazed over, right?
Really?
I'm kidding.
I was going to say, I thought I kept it simple, but maybe there's a few things you can
Yeah, because I would say let's make a simple analog to this.
Okay.
The best way I've thought about it is a battery is a water in a bucket, or sort of a well.
Yeah.
And the circuit being a piping system.
Right.
Yeah, that's probably the best analog, right?
Right. So the whole fluid systems with fluid, like water through pipes, actually model and give you a good intuition actually about how circuits and electricity work. Of course, there's some details in there that aren't completely the same, but it can serve you really well, especially in the beginning if you're not used to it. So basically, what Juan is saying here is you can have imagine if you have some kind of a jug of water, like if you imagine like those ones that you have during sporting events with the little spigot notch, the spigot, yeah, and then the water comes out, So you can imagine if you have that kind of thing, and then you have a tube like a PVC pipe connected instead to that spigot.
I'm not sure if that's a slur or something. That sounds like a slur. Maybe I made it up. Sorry if it is.
Maybe it is. All you spigots out there.
Oh, okay. God. I feel like bleeping that. I'm sorry. Okay, anyway, so go on.
But so you can have a PVC pipe, and the PVC pipe can be various sizes. So the PVC pipe is representing the current, the current wire, essentially. So like the copper wire. And then the spigot, of course, will represent the voltage source, like a battery or something like that. So when you have the water or the current pouring in there, you have different size PVC pipes. The water is going to actually flow through there at different rates. So and electrical current works very much the same way, where you have different instead of I guess actually it does correlate to the size of the copper wires. So you can have big copper wires, and they can let a lot of current in. You can have really tiny ones that let in, a little bit of current.
Yeah.
So the analogy kind of works. And then if you have a big bucket of water, then you have a bigger voltage, we could say.
Yeah.
And that allows for more current to pass through the wire.
Exactly.
But you can still see that if the spigot is small, then it's still going to only come out a little bit of water. So you need to have a bigger and bigger opening for it to actually give you more current.
Exactly.
And then this analogy would be the water.
Yeah.
So it serves the analogy really works pretty can
well.
extend pretty far.
Yeah.
Usually analogies in physics can break down pretty quickly after a certain point, but the water system and then current circuits actually really translate pretty nicely.
Yeah. So this is this is the most simple circuit you can imagine in your mind, right? Because we haven't complicated anything. It's just literally water flowing through a pipe or current flowing through a wire, right? Mm-hmm. No holes or anything. Okay, it's a closed system.
Right.
But we complicate it whenever we add a load, so to say, or a resistance to the circuit.
But not even so much.
No, but this is where Kirchoff's rules come in. Like typically, this guy invented these rules. Well, not invented, but he discovered these tricks in a sense to make sense of the math, I guess. But to keep with the analogy of so the people at home can kind of get a sense of how in this picture of pipes and water flowing or whatever. How does a resistance look like in that system?
Right. So a resistor would be like something like, let's imagine you have your PVC pipe, right? Mm-hmm. If you had a clamp, well, I guess the PVC is kind of a bad one to use now because we're thinking of it like it's a rigid thing. Yeah, let's say instead of a PVC now, let's change it into a rubber hose. So it still functions the same, right? I mean, you change the size of the hose diameter, it's still going to let water in faster or slower depending on how much is coming in. But the reason I want to do that is because if you have a resistor, it's like tying off, let's say, a part of that hose. So you have a section of the hose you can kind of tie off with some kind of, belt or something, let's say. And if you tie off a section of that hose, now the water flow has actually been constricted in some sense. Mm-hmm. So the resistor acts in much the same way for current. So a resistor placed into the circuit actually limits the amount of current that can go through. So you can have a giant, current wire, but if your resistor is really, really large, if your resistance value is large, and resistance is measured in ohms, so if you have a large ohm value, then your current is actually going to be able is actually going to be lesser. Yeah. So your current is going to be a less of amount going through than if you would have, had a smaller resistance value.
Yeah. Yeah. So I think, So this is kind of where this guy Ohm comes in, right? You can like very simple systems. They behave in a way that's, we say an ohmic system is like one where it's V equals or the voltage equals the current times the resistivity of
times the resistance
or times the resistance of the resistivity is the thing.
Because resistivity, like resistance as a func, can be written in terms of resistivity.
So resistance of the whatever you're looking at, I guess. So that's called Ohm's law.
Right. And Ohm's law is kind of the classic circuit equation you definitely want to know. If anything you want to take from this podcast, and you don't know much about it, V equals IR.
Voltage
Ohm's
equals,
law. Voltage equals the current times the resistance. That's the classic equation that would really give you a lot of bang for your buck if you can understand that.
And you could do a little bit of algebra, right? Say you want to know the current, and you have the voltage, and you know the resistance value, and you could just say, you can find the current by putting V over R, right?
Right.
It's a little bit of algebra, but it's nothing too crazy.
Yeah, so if you ever see anything, like if your appliances, you're trying to figure something out like that, you just use regular old Ohm's law, and 9 times out of 10, that'll probably be useful. Of course, your household stuff has AC currents and whatnot, which get a little bit more complicated. But you can probably get away with it with a few things. Yeah, or if anything, give you an estimated value somehow.
Decent estimate. But but Ohm's law is going to be necessary to know in some way. But that's kind of the characteristic equation in working with circuits, I guess. That's one of the more important ones. But then we get to Kirchoff's rules. Especially, we need these rules, especially when you add more sort of load onto the circuit, right?
So load being like a resistor.
Yeah, load exactly, and you get different types of systems or circuit systems, right? You have 2 types, I think, right?
Yeah.
So they call this parallel, and the other one is
series.
Series, thank you. And if you're an engineer, I think electrical engineers probably do this all the time. In fact, I think you can actually when you're at the level of physics we are, this can be modeled using second order differential equations, from what I know.
Okay.
Yeah.
I don't know.
Well, yeah. I mean,
That's all you,
you
bro.
can do this modeling second order differential equations, and it's a lot easier that way.
Okay.
But in the sort of university physics picture, all you really need are these two things: Ohm's law and Kirchoff's rules, and you can solve pretty much any circuit they throw your way.
At least direct current.
Yeah.
So basically a series circuit is one that's kind of the simple circuit that we talked about, where it's just, a battery, a wire, a resistor, and then them all connected in one little loop. And then the parallel circuit would be if you actually added on, let's say you tacked on an extra resistor. It's kind of hard to explain. Maybe I can put it on visually on the screen. But there's an extra resistor or something tacked onto that circuit, but it's not in the same loop. It's actually adding another loop to the circuit. So the interesting thing about the parallel circuit is actually that when you do that, when you add the loop onto its own, you make a secondary loop in the circuit rather than, adding the resistor within that same loop, you actually get more bang for your buck in some ways, where the resistance, the total resistance, is lesser in a parallel circuit than it is in a series circuit that would have the equivalent components. So saying that one more time kind of is
building. Yeah, how do we build intuition for this? Like if you're looking at going back to the analogy of the piping and stuff.
Yeah.
Or the hoses, I guess.
Yeah.
How does that work in that? How does that picture work in that?
So basically it would be like if you have your hose, right? Your normal hose, but you have a junction added now. So instead of just one hose, your hose splits into two different hoses. That's essentially the main part.
I see.
So your current, or the water or the current, gets split. And if they're the same size, the hoses are the same size, they get split evenly. So then your current actually branches off and it goes through each of them separately. And if you imagine with your hose, the reason that the total resistance is lower for a parallel circuit than a series circuit is because if you imagine like in a series circuit where it's all one hose, let's say you got one really, really tight belt on there and then one less tight belt, everything is kind of hindered on that really tight belt.
Yeah.
Because all of the water is going down that one tube. So really the biggest thing that matters is that really, really tight belt. And all of your water is subjected to that really tight belt.
It's being regulated by that first
right
on it. Yeah.
Now if you imagine though that the hose is split, you have one really tight belt on one hose and then one lightly tightened belt on the other hose, then a bunch of the water can get through the really lightly tightened hose. And then there's a bunch of water that's hindered on the really tight hose, but you're going to get more water coming through from the less tightened hose.
Comparatively.
Yeah. So the total resistance is going to be lesser than the series example. So that's so the analogy once again kind of still works.
Makes sense. Yeah.
Yeah. I'm not sure I'm not sure if the resistance values for like a water hose would be the same exact mathematics. I can't remember if that's true or not, but the math is easily derivable. I just was able to derive it earlier, where if you just take into account Kirchoffs laws, where you assume that that the current is divided at the junction, you can use Ohm's law to actually derive the equivalent resistance or what the resistance values should be in a parallel circuit. And you can use the same thing for the series circuit. If you just assume, though, I guess with the series, you kind of have to assume that the voltages are just added together.
Gotcha.
And I don't think that's such a crazy claim. The
voltage is added.
Yeah, like it's a linear combination of the resistances.
How does that make sense in the picture of the analogy of the water?
Of the water.
I'm not sure if it does.
I'm not sure if it does either. I'm trying to think. I think maybe it could, because you could say the water slows down initially from the first less tightened belt, and then it slows down even more from the really tightened belt.
But nonetheless, the total stays the same. right? The total has to be the same, right?
What do you mean the total what?
The total voltage, the sort of total water in the system.
Sure,
right?
sure,
it's not
sure.
Going to be lost unless we're not assuming there's heat generated from this, folks. Okay, let's make it simple.
Let's keep it simple. Yeah.
Let's pretend there's no holes in the piping or anything. Just this is kind of the equivalent. No energy is lost. Everything is conserved. So yeah, the total voltage or the juice in the battery or the water or whatever, none of that's going to get lost, right?
Okay.
So that stays the same. So I guess it would make sense that they have to add together, right? Yeah, it makes sense that it has to be equal to the total, right?
We're not talking about voltage, though. I'm talking about resistance.
Oh, my bad.
Yeah,
Okay.
yeah.
Sorry, I just clipped. But yeah, I get it. I see what you're saying.
Yeah, so the resistance, it makes, it's less intuitive to say, but I think it probably still makes sense. Because the only thing I'm kind of hung up on is if you have a really tight belt, I'm just thinking like really it only matters how tight the really tight belt is. But maybe it doesn't. Maybe it actually does matter if the lesser tight belt before it slows down some of the water, and then the really tight belt slows it down even more. But I don't know. Either way, the analogy is still pretty good for getting yourself a good picture.
Yeah.
And it can extend pretty far.
So how do Kirchhoff's rules even help?
So Kirchoff's rules actually help just because it helps you know how to, like I said, with the parallel circuit, you can literally derive how the resistances should add in a parallel circuit. So the resistances in a parallel circuit are weird because they add as 1 over the resistance plus 1 over the resistance from each line of the parallel circuit. Whereas with a series circuit, it's just the resistance 1 plus resistance 2 plus resistance 3, so on and so forth.
So did you figure out why it's inverse?
Yeah, I did. So it's just literally because of the Kirchoff's laws. So if you just take the assumption that at the junction the current splits, and then you know that the voltage drop, which means that the voltage of each resistor in parallel is going to be the same, then you can literally derive it. You can literally derive the equivalent resistance that way. Yeah. It'll just come out from that. But you need those two assumptions, that the voltage is the same in each line of the wire, which is one I didn't really justify that well yet. Maybe if you guys in the comments want to justify that one, I'll probably justify it to myself later. But then, of course, the splitting of the current.
Yeah. But so basically it falls out from the algebra if you take those assumptions.
Yeah.
Gotcha.
If you take those two assumptions there.
Cool.
Yeah, and that's pretty much it for the Kirchoff's laws. So I guess what I wanted to do next was just talk about some of the other things like Faraday's law and Ampere's law, maybe.
Well, I mean, I want to say before we kind of get too much into like all the other nitty-gritty stuff.
Sure.
Ohm's law also is kind of... Isn't Ohm's law specific to certain types of materials? Like, because there's ohmic materials, you know what I mean? And there's
that sounds more nitty-gritty to me.
Okay, that is kind of weird. Okay,
because that's like... Yeah, because we're assuming linear stuff. Yeah, I'm not trying to get too deep with that.
We are assuming linearity. Yeah. If you think Ohm's law, it's 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 literally the slope value. It's like if you plot V versus your voltage versus resistivity, your current should be linear.
Yeah,
the slope.
Yeah. Ohm's law is a classic, good, nice equation. I don't even know of any ones with electric, but don't follow Ohmic's law, but. I'm sure they're out there. I'd imagine they probably are.
I've worked with some materials that behave ohmic up to a certain voltage, I guess. But,
okay.
Yeah, some might trail off.
Oh yeah, I do know of materials that aren't ohmic.
Yeah,
because they're nonlinear.
Yeah,
when you take the IV curves, which is a current versus voltage graph. Yeah. Then they can look all fucked up and curvy and whatnot.
Exactly.
Which means that the resistance values are not linear.
Yeah, pretty much.
So those would be non-linear ohmic terms, and those are what you would see most likely in real experiments these days. Like any ohmic materials are going to be like non-existent, I imagine now. I don't know if that's true, but the materials I've worked with have been non-linear.
Same. I mean, they've been linear to a certain point. The ones that I've seen,
they eventually go off.
Yeah. But most, these are all approximations that we make anyway. So yeah.
Yeah.
Just as a sort of footnote to that conversation.
Yeah.
But
Yes.
yeah, so the other two principles that are sort of necessary in all this isn't necessarily circuitry stuff, but this is what some would consider electricity and magnetism, which is the study of how electricity behaves.
Yep.
Now,
And magnetism.
well,
But I guess you
electrons,
could say they're
because
related.
electrons are kind of, those are two sides of the same coin for the electron in a way.
Okay.
If you think about, think of the electron as a coin, and those are the two sides of that coin, right?
Okay.
Because electrons are magnetic and electric, right?
Yeah.
Yeah.
Yeah, I don't really like magnetism too much. I mean, I love magnetism,
Magnets,
but
how
I
do they
don't
work?
like it because I still don't really fully comprehend it. I feel like there's still something missing in my mind with magnetism. And I guess I can bring up the interesting thing about magnetism because
Sure.
there's something that you learn in school that I didn't learn why it happened for many years until I got to graduate school, I think. So there's one phenomenon where you have moving charges. So moving charges actually produce a magnetic field.
Yes.
And this is kind of a weird thing because you're like, well, why doesn't a charge just have magnetic field anyway, just stationary? And I guess it does. It does have a magnetic field because we have like a magnetic moment for a proton or a magnetic moment for an electron.
Sure.
But let's not get into that because I don't know how to really deal with that. So
Let's simplify the conversation.
yeah, but if you imagine this, you just imagine a wire, a wire with current going through it. Technically, you have the same number of, let's say you have the same number of positive atoms in that wire as the number of negative, not positive atoms, so positive, you have the same number of protons in that atom. Let's just say we have the same number of protons in that line of wire as the number of electrons. So the wire is kind of electrically neutral, pretty much. If you add an electrical charge, like let's say an electron outside of that wire, there's going to be no attraction. But as we know, or repulsion, as we know, there are like charges attract and opposite charges repel. But since the number of positive charges and negative charges in that wire are equal, then you get no electrical repulsion or attraction. Then the strange thing happens is when you actually start moving that atom or that electron out next to the wire, you're going to get a deflection. And that's because there's a magnetic field that the wire or that the particle takes on as it moves. And the interesting thing about that is that this is actually explained by relativity.
Yeah.
So you can actually explain why a magnetic field arises in a moving charge through relativity. And it has to do with a change of reference. So if you imagine, let's just imagine that instead of let's make the picture even more simplified. So let's imagine you have a proton outside of a line of moving protons. So let's say one's like a line of protons that are moving like a current.
Yeah.
So they're one-to-one, back-to-back protons, and they're just moving along a line. That other proton next to them is actually going to see them. If you think of relativity, it's actually going to see them as being length contracted, and that is because they're moving with some velocity. And because of that, because their length contracted, that means that hold on, let me think.
So let me just tell you right now, folks,
Yeah.
if you don't know this, if you haven't figured it out, the analogy of the piping breaks down.
Yeah, the piping's not going to work in this one.
Yeah, because this is actual physics happening.
Yeah.
Where, like Terence is saying, you get the relative motion of the particle moving and generating a magnetic field, but this is because of the reference frame that you're taking on as an outsider. And a sort of non-inertial, we call it a non-inertial, technically the electron is in a non-inertial frame. Whoever's observing is in an inertial frame. So the electron experiences a magnetic field. No, we would see a magnetic field.
Yes.
So
what happens is, let's imagine you're on the electron. You're moving on the electron. So when the electron, or not the electron, the proton.
Yeah.
the proton is moving, let's say in the opposite direction.
I think you're complicating it.
Yeah, I'm trying to think of a simplified image. I forget how to make it simplified. There's really good videos on this.
Imagine you're on a boat.
I should have I should have drawn a picture so I don't have to sit here just thinking about what the image is supposed to look like again.
Yeah.
But I guess I could just go right to the jump. So basically what happens is you get some kind of length contraction from this, and because the two reference frames need to be equivalent, you need to have the same properties in the other reference frame. There's one reference frame as the other.
It ain't magic, people.
Right. So when one gets length contracted, it means that there's going to be more of an accumulation of charge, because the closer charges get, that means the stronger that what do you call it, the I guess in this case, since it's protons with a line of protons, that means the repulsion is actually going to be, the repulsive force is going to be greater.
Exactly.
Right? Because the distance, the force...
You just shorten the distance, yeah.
Right. The force depends on the distance. So 1 over the distance squared. The inverse square distance relationship is kind of one of these famous things that in physics that everybody kind of knows. And because of that means that you need to account for that when you're switching reference frames. Because when you're switching reference frames, you're not getting that extra force. So then what happens is there's this compensating force, the magnetic field, actually. So you can look at the magnetic field in the inertial frame or the observer frame to compensate for that, that force that manifests in the inertial frame. So it's kind of weird. You actually get this interesting thing where the magnetic field can be explained as an electric field in the non-inertial frame of reference.
So this is like Coulomb's force essentially. It's like F equals Q,
so
squared over R squared.
Yeah, so Coulomb force is all you need to really consider here, and then combine it with relativity. And so you get this interesting effect where you can actually kind of modulate between magnetic field and then electric field. And there's this relationship between them. So depending on how your reference frame is moving in each thing, so you can tune this to where you're actually switching magnetic force or magnetic field and electric field. So it's interesting. I hope I explained that in some kind of way that makes sense.
Yeah.
But
you're saying there's the interrelatedness of it can be the deep physics of this. There's a lot more going on than just this is why the analogy of the water piping kind of breaks down, because there's a lot more interesting physics happening here that can be explained using obviously relativity.
Right.
But yeah,
there's a good example is in Purcell's electricity magnetism.
Right. He kind of opens up with this, I think.
Oh, does he?
In his first couple chapters, I think.
Can't remember.
Which is like the most intuitive way to learn it. So you can Google Purcell electricity and magnetism if you're a deep physics person. But
so it just shows you there's an interconnection with electricity and magnetism. That's why we combine them. That's one of the reasons why you can combine them.
And so there's a lot of deep. But because the electron itself is also a very interesting thing. Like you think about the electron. In fact, whenever I talk about condensed matter physics, I end up at a conversation where I have to explain what the electron is. Yeah. And I have to explain that the electron is electric and magnetic. Like, in fact, the whole angular momentum, you take both the sort of spin, right? The spin plus the, how would you say it? Spin is sort of the magnetic property of it, right? And then you get what I'm saying?
Yeah, so it is and it's not. So I'm a little bit confused about this as well.
Okay.
Because I used to see back in the days, this is something I never resolved myself, and I didn't think to resolve it for the podcast, but sometimes you'll see the spin moment of something is anti-parallel to the magnetic moment of an electron or something. That I don't really get. I don't know if that, I don't remember either if the spin is always anti-parallel to the magnetic moment.
Well, it depends on what spin you're talking about. Like spin of what particle, I guess. Because you can talk about, I guess...
A spin plus or a spin minus, you mean?
Well, I mean, just different... I mean, I guess it depends on the system, really.
Why?
Because you could be talking about the spin of what? The whole nuclei? Like the overall magnetic moment?
But it should still be the same.
I don't know, because Because you think about the total, maybe we might be getting too technical. Actually,
Yeah, I think.
let's not go.
Yeah,
here.
but I think
we can have this
just-
conversation for the Patreon listeners.
but we can still talk about this. But
But let me
I
just
think
say
there's
this.
something. The one thing that's one to resolve is just I don't know if I know spin and magnetic moment are related, but I'm not sure exactly how they're related.
Well, the magnetic moment depends on the spin.
I think so.
It does.
I think so.
I can tell you right now it does.
Okay.
But
I just don't know what that really means. This is one reason why I don't like magnetism, because like there's the intrinsic property of the electron is an intrinsic
Spin.
property is of spin, and the
Yes.
magnetic moment's related to that somehow.
Yes.
But spin is not really a spin of an electron. Like the electron is not spinning at all, so it can't be. It's not going to be able to. You're not going to be able to use the same relativity argument or anything like you did with the.
It's not moving. Yeah.
Yeah, it's not really moving because people have measured this and they've shown that if the particle is spinning and that's where the spin comes from, then it's moving faster than the speed of light, which doesn't make any sense.
Yeah.
So there's some weird thing going on there, and the magnetic moment is like a permanent intrinsic property of the electron.
I mean, it depends on I think you have G factor stuff coming in there, right? And G factors.
I think that's overcomplicated.
No, but I'm saying G factor. It's not gangster factor for the electron. Which electron is more gangster? It's not that. I'm making a crude joke, but yeah. But yeah, they are interconnected. But I think my main point about this was that the electron itself is both electric and magnetic, and its origins are rooted in the fact that the electron itself is the source of both electricity and magnetism in a lot of these systems.
Yeah.
Yeah. So
Yeah, but the thing is, I still don't feel satisfied, even with graduate education, at least 3 years of graduate education.
we can sit down and talk about this.
Yeah, we can. We can sit about it. Talk about it now.
Let's have a whole freaking episode about the electron.
You know what I think we should start doing now in the future
Yeah.
too? I think
Yeah.
we should just stop holding back and start just going ham in
Oh,
it.
he wants to go hard on
Because I'm just being more inspired every day by Eric Weinstein's
Oh, yeah,
podcast,
yeah.
The Portal, and it seems like people are kind of accepting now of just going ham with the jargon. You can try to explain it as well as you can, but I think people are kind of being more interested now in just seeing what it's like for physicists to really talk. And I think even laymen are okay with it now.
Okay.
They'll get something from it. So maybe we should just try to just speak on whatever comes to mind and not hold back. I think we should challenge ourselves to do that
right
in
now.
the future.
You
Want to do it now?
No, I don't.
Okay, yeah, I think we'll start it maybe the next time. We do
I
it.
definitely want to get I want to get into the nitty gritty of because
Yeah,
there's
maybe
some
we could.
very technical topics that we can talk about.
Yeah.
that is that leave us scratching our heads.
Yeah. The only thing I'm a little bit scared of is that I don't want dead air.
Yeah.
Because I know that I think that both of us, we're going to be going too much in our head
processing.
trying to think. Yeah.
Yeah, processing.
And then it's just a matter of dead air. And also, we don't have any tools for mathematics.
right.
Because that's boring as fuck
This
for
is
a
where
podcast.
this is where math. This is why people invented math because you're imagining things in your mind that are very abstract, and you need to write things out to see them symbolically, right?
And there's certain relationships that and capture and really powerful identities and equations and things that make it so much easier to come up with conclusions that it's like you're just stacked. You have a bunch of information and relationships stacked in your brain.
Yeah.
But sometimes these things are not obvious until you go through the rabbit hole and then actually see,
Connecting the dots.
yeah, there's something there that I didn't consider.
Yeah.
But of course, we're not going to kill you guys with math on a podcast because that's just not even. It doesn't make sense, especially because it's an auditory format.
Yes. Yes.
It just doesn't work.
This is radio school. 101 YouTube University.
Yeah,
101.
we should try to keep it as conceptual as possible, but
You're saying I'm not afraid to go down this road.
yeah, if we can go down the rabbit hole, we should. But if we're feeling like, oh, damn, this is even too deep for us, let's turn back.
Yeah. Well, I mean, we kind of did go down the rabbit hole a little bit with the relativity one. That was.
Yeah, I didn't like it though. It wasn't that good. I feel like I could have done it better.
Okay. We'll
But,
just chalk it up to the time.
Yeah. Well, I think it's also because of just me having brain freeze.
Well, because it's late in the evening. And by the way,
Yeah.
me and Terence are still recovering from
Denver.
Crazy weekend at Denver.
Yeah.
Crazy week at Denver because the time changed too, and the fact that we took a red eye.
Yeah, we basically drove like after we flew and we landed at 6 a.m. We drove another 4 hours.
Broken sleep in between.
Yeah,
like
so
an
it was
hour.
kind of rough, but at least we got to do rotations on the road and whatnot.
Yeah,
It was easier.
yeah. It wasn't bad, but yeah, we're still recovering, and hence your boys staying up kind of late doing this podcast because of me. So,
But anyway, let's get back on topic.
Oh yeah, yes,
yeah.
We have so to kind of wrap this up, I guess.
Are you trying to wrap it up already?
No, bro, we're doing 45 right now.
Okay.
Yeah, we're doing pretty good on time.
All right.
But but I feel like we would end with this because
It's going to be long.
because we can definitely get into this one. So,
Okay. What is the next
well, the
one?
last two things are we didn't even touch on what we wanted to touch on, which is actual E&M stuff.
Well, we got, we can do a podcast on E&M stuff. I just wanted to kind of do some things related to circuits specifically and maybe some cool concepts. And even if you can think of anything related to circuits that you kind of are interested in.
Well, because you said you wanted to mention other sort of physical laws like electricity and magnetism.
We can.
You said Faraday's. You said there were two
Sure.
important laws.
Yeah, so I picked Faraday's law and Ampere's law just because they're usually related to circuits a lot of times. Like Faraday's law is the one where basically if you imagine you have a magnet and a loop of wire, a loop of current producing wire, you could say. So like some conductive wire. You can put a magnet through it, and then when you put a magnet through that loop of wire, you can actually induce a current. So the magnetism of that bar magnet is actually causing a current to exist in the wire.
Yeah, and you can do this. You can do this experiment at home. It's a very rudimentary
easy
experiment.
one. Yeah, extremely easy.
If you want to blow a child's mind.
Yeah, this is like. Well, I don't know if they'll appreciate it though.
Oh, they will.
You think? Oh,
because remember, they think about a battery. It needs to have a battery connected to get power.
True. If you just put like a little light bulb on it, like an LED or something, and then they show it lighting up like that, that's kind of cool.
Or if you put a magnet inside of your body, then you could really blow their mind. Say like it's surgery.
Doesn't sound very healthy.
Well, there's a guy that actually put magnets in his fingertips or on his. Surgically, he put magnets in his body so that he could sense magnetic fields.
Wow!
So he adapted. So his body adapted.
Imagine him trying to imagine him trying to use his cell phone.
Or imagine him trying to open a refrigerator door. He's like, "How do I get?" Yeah. Anyway, I don't know where that guy is.
He's just using his looking down at his cell phone, just like typing like this. Like
Not
3
even
feet
touching the
away.
screen. Yeah. I want to do a "Where Are They Now" episode.
Didn't we do we did an episode on cell phone on smartphones too?
Yeah, we did. But I want to see this guy. Where is he now? What is he doing? But basically, this guy had a brilliant idea of putting magnets on his body to sense magnetic fields and stuff. And so, in principle, this guy could do this experiment and amaze his. I imagine he doesn't have children for obvious reasons, but. But he can impress his nephews or nieces at parties by doing this trick. And all you really need is a conducting wire, like copper or something, and a light bulb, and of course a magnet or something.
Right.
But yeah.
And using the Faraday's law, just put that wire in a loop, put the magnet through, I guess his finger in this case, and then it lights the light bulb up.
Yeah.
So yeah. And that's also related to Lenz's law too, the whole Faraday's law. But I don't think I want to get too much into Lenz's law.
Lenz's law is kind of nuts, isn't it?
It's pretty much like Faraday's law.
Yeah.
I don't really know too much of a distinction between them, actually.
Well, it's just like how you induce. That one's about inducing a voltage difference, right?
Yeah, but that's what Faraday's law does too.
Pretty much, yeah.
Yeah. So I don't really know. There's probably some minor.
Well, that one just blew my mind.
Yeah.
So
yeah,
whenever you think about like your house, right? You ever notice how when the AC kicks on, the power dims? Or like if you have a compressor for something, the power
sometimes,
dims.
yeah. Depending on not in my house, but sometimes.
Oh, it does. It happens.
Really?
I have the compressor for I have a little mini fridge, and
you notice
if you go back to listen to old episodes, you can hear it kick on a couple times.
Oh, I didn't notice.
What you'll notice though is that sometimes you'll notice that your light dims momentarily, and if you notice that's because of Lenz's law, because the compressor kicks on. And because it basically induces a change in EMF, and the circuitry in your house is like, no. And so it kicks back the other way. So momentarily, it kind of reverses, or well, not reverses, but basically it tries to change the direction of the current, and then basically the overall house, the circuitry in the house is like no. And,
I see, but I could imagine that you can have capacitors to hinder that somehow.
Maybe, but
Okay, but I don't know though.
But no, but basically, if you see this in most people see. I saw it a lot as a kid too. I always wondered what that was about because, and you'll see this in buildings too, in office buildings and stuff. If the AC turns on, you'll sometimes and you'll know because you hear like a something, a switch, and then you'll see the lights dim a little bit. That's because of Lenz's law. Right. Really cool stuff. But yeah, I mean this. Yeah,
but that didn't really explain what Lenz's law is.
No, well, it's basically it's a law of physics that says, or a law of nature that says, any change in the potential will be met with it's a sort of equal and opposite sort of change, right? It's kind of like Newton's third law or Newton's laws for
in some way
for EMFs.
The connection's not so obvious though.
Sure,
if you aren't familiar.
Okay, what's a better way to put it then?
So I would just say that when you have a changing magnetic field through an area. So it could get really complicated with the terminology and jargon with this, but I'm trying to keep it simple. So with Faraday's law and Lenz's law, you can almost think of it in the same kind of vein. So as I was saying with Faraday's law, when you have a bar magnet passing through the wire loop, Lenz's law is basically saying that as the magnetic field increases or decreases through that wire, you're going to get a current induced in either direction, depending on if the magnetic field is increasing or if the magnetic field is decreasing. So it kind of makes Faraday's law, I guess, more specific. Honestly, I'm not really sure on the detailed differences between Faraday's law and Lenz's law because I kind of think of them as the same thing.
Well, one of them is basically from Maxwell's equations. The Maxwell's equations are the sort of 4, maybe 5, if you want to include the. Why am I blanking on the force?
5.
F equals Q E.
Oh, that's Lorentz force.
Thank you.
Yeah, I don't think anybody considers
it's been
that
a long
as
day.
Maxwell's equations.
No. But Maxwell's the important equations in E&M. Maxwell's equations and Lorentz force.
Right.
But yeah, so Maxwell's equations, you can actually derive the EMF relation, the EMF force, and the Lenz's law essentially. Okay. Yeah, for you listeners out there, I guess.
For Maxwell's equations, you really should be able to derive like everything in E&M. That's kind of what the whole point of Maxwell's equations are. Yeah. So like Maxwell's equations are supposed to be like the complete picture of electricity and magnetism.
Everything else is boundary conditions.
Right. Of course, I don't really I feel like maybe it is, but maybe I just haven't explored them to the fullest extent. But like there's certain things about like the connection between magnetism and electricity and like light. There's certain holes in my knowledge that I'm not satisfied with.
We could do a Patreon thing for that.
Like have our holes filled in.
How to derive cool stuff using E&M.
Oh yeah, we could do that
using Maxwell's equations.
That'd be interesting. Yeah, so we can have like just
gatekeepers of knowledge right here, people. all the cool tricks we've learned.
Yeah,
so you can impress your physics friends.
We're trying to give some value to the Patreon for people to feel motivated to go on. But it's in the works. We'll see. It's in the works.
That's a really cool thing because you and I know a couple tricks how to derive certain things.
Like we do. We know a lot of tricks.
Yeah,
I think we get hung up mostly on trying to find new tricks though. So maybe we could do that one day.
Yeah.
But yeah, I mean now, and also we didn't even address the audience. This is our house now. So this is my house, and Juan is now living here too.
Yeah, I'm living here.
So we are officially in the Eigen cave.
Yeah, we are officially in the Eigen cave.
We don't know if this is going to be the complete setup though, because it's kind of
under construction still.
Yeah, we're trying to figure it out as we go. I guess you can't really see the junk on camera. That's good.
No, that's good. Yeah.
But there's some junk around here.
Mm-hmm. Yeah. Yeah. They don't see anything behind the cameras.
Yeah. Thank God.
Yeah.
But yeah, we're trying to figure it out still, and hopefully we can try to crank out some more videos. So we've got some ideas. I don't want to say too much, so we don't overpromise and underdeliver. But we want to start doing some more stuff, and so stay tuned.
Stay tuned. If the corona doesn't wipe out, 10% of the population, we should be okay.
Yeah.
Yeah. So
at least not our listeners. But go ahead.
No, it should be fine. But yeah, I think there's some really cool stuff that can be done. Like a lot of this is just is
What's the time?
based off E&M, I guess. And so, man, there's so much to do with this and with this E&M stuff. Now I'm kind of caught up on that.
Yeah.
But I guess look forward to that. And I think we'll announce it on Twitter probably.
Yeah, we'll make announcements if things come up.
Yeah. So yeah. How are we doing on time?
I don't know. I think we're probably
right
at least hitting an hour.
53. Yeah, we're good. We're good to stop here. I think because
the
the other
no needs to force it.
No, because the other thing was Ampere's law, but Ampere's law is kind of
Yeah, we can just say it real quick.
pretty basic.
Ampere's law, it's not super basic. It's not obvious.
No, it's
It's
not.
not trivial. Like deriving it is not a thing I would say is trivial.
Oh
but,
no, actually, you can derive it using like gauge
transformation and stuff.
Yeah.
It's easy if you do it with Maxwell's equations,
Yeah.
but it's not easy to if you don't know Maxwell's equations. You're trying to do from first principles. It's not that simple. I don't think.
No.
But basically, it's just relating B field to the current.
Mm-hmm.
That's the long story short. It just relates magnetic field to current.
Yeah, and you can do some very special relativity to derive this too.
Yeah.
By choosing a gauge, an appropriate gauge transformation, and you can get to pretty much deriving Ampere's law. Ampere's law.
Okay.
So, and they did that. They did that in one of our classes. One of the legendary professors, one of the harder professors at the university.
Oh, okay. I don't remember.
That
was something I
he did
put
that
out
the
of my
first
mind.
semester. Well, I mean, it was an early class,
Yeah.
so I get it. But I was like, wow, that was like cool. That's kind of cool. But maybe we might show the derivation of that if you go to eigenbros.com. You might be able to.
We got a
find
bunch of stuff we can derive.
Yeah,
Yeah.
a lot of cool stuff.
Yeah.
So if you're interested in that, email us, I guess, right?
Yeah, we got an audience actually that knows some math too. Like I did some survey polls back in the day, and there are people who know math.
Cool.
I was trying to gauge that to see if we should even bother really doing math stuff. I'm not really sure on the engagement of mathematics stuff on our website, though. I have a feeling it's kind of low because I put up some problem sets and solutions on the website, from our homeworks in the past, but. I'm not sure how receptive people are to that because I don't have any good metrics on the website yet that I can actually read that. But if you guys want to see more mathematics, let us know. What's a good question we should leave off on?
Do you want to see? Okay. There's a lot of questions I could ask, but we could do so many topics about Maxwell's equations. We haven't even talked about that. That's like a huge thing.
That's a giant one.
And even the nature of the
electron. I'm a little
electron.
scared to do that one, actually.
The nature of the electron is so it still leaves us scratching our heads, collectively as scientists. Not even scientists, but just physicists as well. But
I feel like we'd have to do some real good research on that because I don't want to just be talking out of my ass on a podcast.
No, of course not. But it's still there's some things that just escape us. In fact. Maybe this will leave you curious, but for the most part, we assume the electron is actually a point particle, and realistically, it's kind of it has to have volume, right? It has to take up space. But the thing is, most approximations, I think.
I think that's just a matter of scale,
effective, right? That's an effectively, but the electron does have volume. But in a sense, I think most of our calculations, place it at that would essentially confine the electron because the electron is such a weird thing. It has it's a wave function. It can be described as a wave function of something, and then we describe it as a point particle in other instances, and it's kind of strange.
I think it's just a matter of scale.
Okay,
because when you have point particles, it just means that your scale is really you're looking at a macro scale system where you can effectively call something a point particle.
So
because you can do with a marble even.
Yeah, for me, if I look at a picture of the Earth, right? And I say,
it's a point particle now.
Yeah, so technically that's for me that's a selfie, but from a very far distance.
Wait, I missed that one. Was that supposed to be a joke?
Yeah.
Okay, I missed it.
I'm basically saying when you look at a picture of Earth, you say, that's a selfie. It's just a very far global view of me.
Okay.
It's it's not even a joke. It's just
I'm sorry, what I couldn't.
It's not even a joke. It's an observation, but it's fine. Anyway, it's too late. It's too late in the evening.
Yeah, it's late. We'll give you that excuse.
It's late.
Juan did do stand-up in Denver just to...
yeah, I did stand up in Denver. I don't know if I said this. It didn't go well, for obvious reasons. But yeah, anyway, I guess my question is kind of circling back. Do you want to see something on, like, I guess, out of those two topics, which one seems more interesting? Us talking about the electron, nature of the electron, or maybe content that even leaves us kind of confused? Like, do you want us to cover stuff that we don't know?
Damn, that's a long list.
I mean, that's cool, but that's like...
That's a good question. Let's formulate it to this.
Yeah.
Do you guys like it when we talk about things that we are confused about? Or do you guys prefer to hear us talk about information and facts that we are really confident on? Because I think we tend to go towards a little bit
topics that we know about.
Yeah, we go a little bit in between. We usually run into things we're confused, and then we circle back away.
Yeah.
But I think we tend to try to stick to facts. I have a feeling that I feel like we're probably going to have more interesting podcasts if we talk about more confusing topics.
Yeah.
But those are scary because I feel like we need to be well prepared for those.
Yeah, because the community, the physics community, let me tell you right now.
Yeah.
Savages.
Yeah, they'll destroy us.
Barbarians.
But we got to take the brunt, you know?
Barbarians. They'll attack you. It's like they smell blood in the water. They're like sharks.
That's good, though.
Because there's always somebody that knows. There's always somebody who's more specialized in this specific topic than you.
As long as you're not misleading
Yeah.
into a crazy off the wall area,
Yeah.
then I think you're okay. And as long as you also qualify what you don't know with I don't know, or you say I'm speculating that this could be this such and such. Just be careful with your words, and I think it's okay.
Yeah. Cool.
All right.
Yeah, that's about it.
Okay, guys.
Thank you.
Thank you, guys.
For making it this long. I hope that you actually took the time to write down your question, type it, or hit send on Twitter. Let us know. Give us feedback on that. Because we definitely would like to talk about. I mean, it's more interesting. What is more interesting, right? Talking about stuff we're confused about, or talking about stuff that we do know.
Yeah.
Or maybe still kind of teetering the line, right?
Yeah.
So let us know.
Sounds good. And I guess once again, guys, just check out the website, Eigenbros.com. We've got math and physics problems on there, as well as the the usual podcast stuff. And then also check us out on Twitter at Eigenbros. Check us out on Instagram at Eigenbros, and then also TikTok, Eigenbros2. And we'll see you guys next episode.
Peace.